Hey guys, these are the video solutions for the practice test that we're working on. I'll probably go over the first few problems and then make a video for the rest of them. So number one, we're talking about an object with a mass of 15 grams, which is which is 0.015 kilograms, right? We always want to be working in the same kind of units. It's acted upon by a force of 30 newtons. So remember, 30 newtons is kilograms meters per second squared. And we want to know what is its acceleration. So in this case, we need to use Newton's second law, which is force equals mass times acceleration. This is the mass, and this is the force, right? So we're going to put 30 newtons equals 0.015 kilograms times acceleration. We don't know acceleration. We could also go ahead and change this to kilogram meters per second squared. We're going to solve for a, which means we're going to divide both sides by 0.015 kilograms. And so this ends up being a equals 30 divided by 0.015 is 2,000. And then what would happen is the kilograms here would cancel out the kilograms there, and we have meters per second squared, which is how acceleration should be measured, right? Is in meters per second squared. So in this case, we get D. Number two is which statement about the mass of the falling object is correct? A, it decreases as the object falls. B, it is equal to the weight of the object. C, it is measured in newtons. D, it stays the same as the object falls. This should be D, right? Weight is measured in newtons, not mass. Weight is not the same as mass, right? Weight is mass times acceleration. Weight is a force, right? Weight is mass times acceleration. And mass is not going to decrease if you're falling, right? Mass should stay the same unless you remove something from it. So that one should be D. In the following free body diagram, the motion of the block is best described as A, accelerating, B, decelerating, traveling at constant velocity, or traveling at constant speed. Inertia says that an object in motion should stay in motion unless acted upon by an outside force. Sometimes we have a net force of 0, meaning the force on both sides is equal. That if that was the case, it would look like this, right? And if it looked like this with this red arrow, then it would be traveling at a constant velocity, right? That wouldn't be changing because the net force is 0. But as you can see, this arrow here is bigger, which means the force in this direction, in the upwards direction, is greater than the force in the downwards direction, which means this thing is going to start wanting to move upwards. Now, we don't know something about this block. For all we know, right now, it's moving downwards already, right? Pretend it's already moving at 50 meters per second downwards. Then this force pushing upwards is going to start slowing it down or decelerating it, right? So B is an acceptable answer because it depends on which way it was moving, right? If this object was already moving up, right, before we looked at it, then it's going to continue moving up in a faster way, in which case it's accelerating, right? So decelerating if moving down, and accelerating if moving up, right? Two different answers there. Two metal balls are the same size, but one weighs twice as much as the other, right? Same size. Maybe this weighs 2, this one weighs 4. Again, weight is a force, so it'd be like 2 newtons. They're dropped from a 2-story building, so imagine you have a 2-story building over here. The time it takes the balls to reach the ground is, which one's going to hit the ground first? The idea is that it should be about the same for both balls. if you neglect air resistance, right? The only reason the 2 Newton one would go slower is if there was a lot of air resistance pushing it back up. This one would be able to cut through the air better than this one would because of its higher mass, right? So C is the correct answer there. Okay, for number 5, we first need to understand what it says because it's kind of confusing. Basically, we're dropping a ball, right? It has mass m, and the ball is going to hit the ground and then rebound back up. And this graph here shows the situation, right? So this is the velocity of the ball, and then here is the moment at t1. This is the moment where the ball hits the ground, right? So the ball hits the ground at t1 and has a velocity of v1 when it hits the ground, right? And then it's in contact with the ground for a little while, and then at time 2 it bounces back up and has a velocity of negative v squared, right? And so what we need to do is we need to try to find out which one of these represents how much force was exerted on the ball, right? And so we want to think, okay, how can we relate force to the situation? Well, each of these balls had momentum before and after, so you might say, okay, momentum, which was with P, equals mass times velocity, right? So you could say, okay, the momentum before, I'll use a B, was the mass times V1, and the momentum after, I'll use an A for after, was mass times, here so it's negative V2, so negative V2, right? And so the momentum before was this, momentum after was this.
She's like, now? I'm like,
V2, negative V2, which could also be expressed as negative M times V2. And then what we want to know is what's the change in momentum, right? So the change in momentum would be, how did the momentum change? Well, you could always just do P of A minus P of B over T2 minus T1, right? Because you're trying to find over the change in time. In this case, the change in time is found by doing T2 over T1, and that will show you the change in momentum. If you do this, you end up with this, which is, hold on one second. Okay, never mind. We're not going to do it like this for now. Sorry. We're trying to look for the force, which that's not necessarily going to give it to us. What we want to think about is change in momentum is basically the same thing as impulse, and we had an equation for impulse, which was impulse equals force times time, and that's the same thing as change in momentum, right? So if we're looking at, and we're basically what we want is the force, right? We want to be able to figure out the force, so we're looking for force. The force is going to be equal to the impulse over time, and remember, impulse is the same thing as change in momentum, right? And so the impulse here would be basically the momentum before minus the momentum after, right? So in this case, momentum before, we had it over here, was mv1 minus the momentum after is mv2, right? I'm putting the negative here because of what we had here. And then over the time, we want to think how much time did it take for this to happen. Well, it occurred between T1 and T2, so it's just how much time occurred between those two times. So it would be T2 minus T1, right? And so then you can work this out and you can get, this is going to turn to a plus sign, right? So now you have mv1 plus mv2 over T2 minus T1. And you can factor out an m here, right? So we're at m times v1 plus v2 over T2 minus T1, and that is your force, right? And so you can see which one of these matches that. Well, D matches that. All right. Okay, number 6 is talking about this fan thing. The fan is mounted on the car, right? And then there's a sail on this cart as well. And the fan starts spinning, pushing air this way, right? So you want to think what's happening. Well, you might think, oh, the air pushes on the fan, on the sail, and then this car starts moving, right? That's like, I think that's the most common answer. But you have to realize that as the fan pushes on the air, I don't know if you ever held like a fan without it being on a stand, but like as you hold it, it also pushes back on you, right? So Newton's third law says as the fan pushes on the air also pushes on the fan, right? So there's also this force going this direction that's equal to the force that the fan pushes out the air. And my pen is doing an awful job of writing right now, right? So that force the air pushes on the fan is the same as the fan pushes on the air. And because the fan is lodged on the cart, it's not going to move, right? This would be very different if this fan were on the ground, right? If you put the fan on the ground, then yes, that cart will move because the air pushing on the fan will keep the fan at rest because it's secured in the ground. But then this force of the air will push the cart and it will move forward, right? So the correct answer here is B. It remains at rest because the fan is on the cart. Okay, number 7 is a ball is released from here and rolls down a track from the position shown. What is the furthest position the ball could reach, right? So the ball is going to go down. Keep in mind right now it has a lot of potential energy. Why can I not write? It has a lot of potential energy, but no kinetic energy, right? Right now the kinetic energy is 0 because it's not moving, and the ball is moving down. It's converting that potential energy to kinetic energy. At A, it has its highest kinetic energy, and then it starts converting that kinetic energy to potential energy because it starts gaining height. However, there's no addition of forces, right? Nothing's pushing the ball. So the highest it could ever reach again is as high as it was when it started. So the highest it can reach is B. It will move fastest here, and then it will basically stop when it gets here. So the farthest it can reach is B. I think I forgot to paste the question options. All right, no, I didn't. That's just that. All right, so next one is a ball of mass 2 kilograms falls vertically and hits the ground with a speed of 7 meters per second, as shown below, right? So this ball weighs 2 kilograms. And my pen is really doing a number today, 2 kilograms. Wow. Anyway, and it hits the ground, and then after it has a speed of 3 meters per second, they want to say the question is the magnitude of the change in momentum of the ball is. Okay, so basically we're thinking the ball, as we're talking about momentum, so momentum is P. Oh man, this pen is really, just give me a second. Okay, let's try this again. Momentum, come on pen. Momentum, which is given by P, is equal to mass times velocity. So this thing has momentum before and after, right? So again, we could write this, the momentum before momentum before. All right, I'm going to have to do this one in another video, so just look for this in a different video.